This is an intro on how to do contact angle measurements using the dropometer. We begin by first opening the app. We first have to create an account to store all the projects. Now we are ready for our first experiment. In this window, the image calibration number is the outer diameter of the needle. The differential density is the density of the liquid within its surrounding medium. In this case, since it's water and air, we can leave it as its default value. After creating the project, insert the phone into the apparatus. The first step is to focus the camera on the droplet. It is important to focus on the droplet and not the needle or the edge of the substrate. We do this by first generating a small droplet and then adjusting the focus on the phone. We use a combination of the LED backlight and the lighting on the phone to get a crisp contrast between the droplet and its surroundings. Once the satisfactory image quality is obtained, you simply capture the image and proceed to the analysis. From here, we drag the horizontal bar to where the droplet meets the surface. This is known as the baseline. From here, we position the 2 points to locate the contact points. This does not have to be accurate, as the algorithm will find it by itself, but we just give it an initial guess. Due to the needle being too close to the left side, it slightly throws off the contact point. So for the left contact point, it's slightly off. To fix this, we simply switch to the extended points method to recalculate the droplet. The extended points method will force the algorithm to measure the contact angle from the user-defined baseline rather than algorithmically by itself. Now we will measure the contact angle of the droplet using the Young-Laplace algorithm. Unlike the polynomial algorithm, where the needle can be inside or outside of the droplet, the Young-Laplace algorithm requires the needle to be outside of the droplet. It should be noted that because the droplet was given time to evaporate, the contact angle is now different. We will now compare the polynomial values with the Young-Laplace values. The Young-Laplace algorithm requires an initial calibration. When we first started this project, we inputted the needle outer diameter. We simply use the needle to get the calibration number. To get proper results, make sure the calibration number is green. If the number is red or yellow, there is something off, or something was not done correctly and must be redone. You will notice that both the left and right contact angles are the same. This is because the Young-Laplace method assumes that the droplet is perfectly axisymmetrical. However, this method also gives us values for volume and cross-sectional area. We will now do a measurement of the advancing and receding contact angle. Note, the previous measurements were static contact angle measurements. The contact angle can be anywhere between the advancing and receding contact angle. So to define a surface properly, it is recommended to always report the advancing and receding contact angles. To advance and recede the droplet, you simply have to increase the volume of the droplet and decrease it. The observed behavior will be as follows. As you increase the volume of the droplet, the contact angle will increase, but the droplet will not advance on the surface. After a critical value is reached, the contact angle will remain constant and the droplet will keep growing on the surface. The same is true for the receding contact angle. At first, when you reduce the volume, the contact angle will start to reduce until it reaches a critical value, and from that point on, the droplet will start to recede from the surface. We will use the multi-capture function to capture multiple images. Simply put, we input the number of images to capture and the duration of each capture. So 20 images in 20 seconds is 1 image per second. This phenomenon can be observed on the left side of this droplet. As the droplet's volume is increasing, it is spreading on the surface, with the droplet contact point moving further away from the needle. The reverse is true with the receding contact angle. As we recede the droplet, the contact point is moving towards the needle. We call this a moving contact point as it is unpinned from the surface of the substrate. Now we're going to analyze the images. The first thing we'll do is go to the first image and use the vertical lines to locate the left and right contact points. Looking at the image, it can be clearly seen, more so with the left than the right, that the contact point has advanced, since both contact points are now further from the needle and no longer in the original positions. Repeating the same measurement for the receding contact angle, we now have a range for the possible values of the contact angle. The processed images can be saved either to an SD card or a cloud storage. Simply select Save to Cloud Storage and select the service. Then simply press the Save button and link the service to your account. Visit our website at dropletsLab.com to learn more.